All right, let's talk about section 15.4 and look at Green's theorem. So we begin the section with a theorem, commonly known as Green's theorem. Let R be a simply connected region with a piecewise smooth boundary oriented clockwise. That bears a little bit of explaining. Remember, whenever we have a contour, we're giving it by a vector valued function, and so it's parameterized, usually by a vector, by a parameter t, although theta or any other symbol can be used. Because it's parameterized, it comes with its own orientation. It makes a difference if I'm taking a vector from here this way or from here back this way. So here we're saying we want a piecewise smooth boundary that's oriented counterclockwise. So here we want something that looks like this. Here we want a simply connected region, meaning no fair having multiple pieces out throughout, one here, and one over here. It should be one simply connected region. And with a piecewise smooth boundary. Here it's okay if you have a cusp here or a cusp here, but you should be able to cut it into a countable number of smooth pieces. The orientation should be counterclockwise. So here, if you're starting from this point, you would be going around this way, counterclockwise. My mistake, counterclockwise. What can I say? I have a digital watch. So counterclockwise, the way we usually count angles in trigonometry. One way of thinking about counterclockwise is imagine that you are on a little car right here, and you're facing in that direction. The region in question should be to your left. And I got to say, I'm getting so much use out of these little guys. Here, if you imagine that this is a track, if you're going around, you're facing in that direction. Notice that no matter what, the inside, the region, is always to his left. All right? So this would be your region R. Okay, so let R be a simply connected region with a piecewise smooth boundary along the outside that is oriented counterclockwise. Okay, so we have a region, and aside from what we usually have, the stuff inside the region, here we're also saying something about its boundary. Okay, now let M and N be functions. Here we're doing functions of two variables, x and y. Let M and N have continuous first partial derivatives in an open region containing R. So here, my M and my N have continuous first partials out here on the plane, and maybe it's not the whole plane, but it's definitely something that involves this. It's definitely, M and N definitely have continuous first partials in here, and probably elsewhere. If all of that's the case, if you have a region which is simply connected with a piecewise smooth boundary oriented counterclockwise, and M and N have first partial derivatives in that region, then the line integral of the vector field M comma N dr, or in its differential form, the line integral of Cm dx plus N dy is equal to the double integral over the region R, that might be a little unexpected there, the double integral over the region R of the partial of N with respect to x minus the partial of M with respect to y, all over the differential of area. Right? What this theorem essentially says is, you can't judge a book by its cover. You can't know what's going on inside by just looking at the outside. Except, yeah, you can. That's exactly what you can do. You can tell exactly what's going on inside of this region as long as you know what's going on right on its boundary. Or, conversely, you can know everything about what's going on the boundary if you know what's going on inside. It turns out that as long as you know how to relate them, what happens on the outer edge and what happens on the inside are exactly the same. Right? So this is not at all obvious. Why should that be the case? Why should it be that the stuff inside is exactly equal to what's going on around the line integral on the outer boundary? This is not at all an obvious statement. So this one, we really do have to prove this one. Okay? So let's begin by assuming we have a connected, simply connected region with a boundary that's oriented counterclockwise. And we're going to go ahead and split it up two different ways. Okay, so here's what it would normally look like. But here, I'm going to go ahead and split it two different ways. So I'm going to go ahead and just draw my boundary. Okay, and I have my stuff inside. I have my region R. And what I'm going to do is I'm going to look at this from two different points of view. I'm going to look at it as a top along with the bottom, and I'm going to look at it as a left compared to a right, something like that. Okay. Here, this might make a little more sense if I give this a coordinate system. Here's my my x-axis and my y-axis, and same thing over here. So here, these aren't meant to be two separate regions. I've just drawn the same region twice. It may not be apparent because my illustrations don't, they look like two completely different potatoes as opposed to the same potato. But here, I'm really just drawing the same region twice. This is meant to be the same R, but I'm looking at it from 2 points of view. The first point of view, I'm looking at it this way. I'm going to say, I'm going to start from this point, and you say, why this one? Because it's the one on the left. Left to right, A to B. So here I'm going to take this, and it's going to take me all the way from A to B. And then once I've done that, I'm going to take this upper contour, and I'm going to let it bring me back to A. Okay. So for right now, we're going to look at just this illustration. I'm going to call this, let's say figure 1. And I'll call this one figure 2. And I'm going to use these one at a time, and each one will prove something which when we put together will give us our full theorem. Okay. Okay, so consider the line integral m dx over c. So consider just this part right here. Okay. If we consider just that part, well, that's split up into two regions. After all, this is my contour C, which I've just broken up into two separate sections. Here, let me call this C1, and I'll call this one up here C2. So this contour is given by, really, it's the sum of these two. So it's going to be C1m dx plus the integral over C2m dx. And if I add that one with that one, it gives me the whole contour. Okay, straightforward enough. All right, now I can write this by substituting in what we learned from these boundaries. Namely here, this lower curve, I can call this just a function y as a function of x. So here's C1. I can consider this as being, well, my y value is a function of x. And up here, I have my y value as a function of x as well. And of course, those are two different functions, so I'll call this one f1, and I'll call this one f2. Okay, so right here, I can write this as the integral from a to b, Notice, if I just take that upper curve, this is just a regular integral over the x-axis, the way we've seen since Cal 1. This is just a regular integral from beginning to end of, well, now m is a function of two variables. It's a function of x and y. Well, yeah, but it doesn't have to be. Look, we can write y as a function of x as well. So we can just make the whole thing a function of x. Normally, we would say this is m of x comma y, but we don't have to write it as x comma y. We could write it as x and f1 of x, which makes the whole thing just a function of x. And over here, I could write this as pretty much the same thing. After all, that's going to be m of xy, but again, up here for this second contour, I'm going to use y is equivalent to f2 of x dx. And now here, instead of going from a to b, now I'm going from b back to a. Okay, just like that. But now these are just both regular old integrals from Cal 1. It's a function of x, and I'm integrating with respect to x. Well, notice these boundaries are the same. Well, almost. One is backwards. Oh, okay, well, let me flip it. After all, we learned in Cal 1 that you can flip boundaries of integration by taking the negative. The integral from b to a is the negative of the integral from a to b. of mx comma f sub 2 of x dx. Okay. Oh, but now since these both have the same boundary, I can stick them together, and I can write this as the integral from a to b of m of x comma f sub 1 of x minus m of x comma f sub 2 of x dx, just like that. Now consider the double integral over a region R of, let's see, I started with m, so let's go with this one, of del m del y dA. All right. Well, now that has nothing to do with a line integral. This is the double integral. We're back in chapter 14. We're taking I guess this would be back in chapter 13 when we first talked. No, that would be double integral, chapter 14. So here, we're looking at a double integral of the stuff inside. And remember how we find a double integral? We're going to write this as an iterated integral. And let's see here, that's going to be del m del y. And here, by Fubini's theorem, we can say, well, dA is dy dx. Here, we want to use x as our outer boundaries, because notice x here is described by just a couple of constants from a to b. Okay, it's from a to b. And y is given by a couple of functions. But those functions happen to be functions of x, which is the outer boundary. Oh, okay, so that's going to be, well, let's see, that's the lower one up to the upper one. So that's going to be f1 of x up to f2 of x. Okay, so this is just a double integral. All right. By Fubini's theorem, we can write that as the integral, the iterated integral of del m del y. First with respect to y. Well, we're doing y first because that one depends on a couple of functions. And then with respect to x, because x can be bound by constants from a to b. Notice here, though, that you're integrating the derivative of y with respect to y. Right? That's del m del y integrated with respect to y. That's just m, right? The derivative of the antiderivative with respect to the same variable. So here we can write this as the integral from a to b of this stuff right here is just going to be m evaluated from f1 of x up to f2 of x dx. Right? Okay, well, now remember, m is a function of x and y, and here we're plugging in y is equal to something. So x is going to be left alone. So this is the integral from a to b of m of, again, well, we haven't gotten to x yet, so x just stays x, but we're substituting in these in for y. So we're going to take f sub 2 of x, like that, minus, and then we're going to plug in this one down here, that's m of x comma f sub 1 of x dx. But notice that's exactly the same as this, except they're backwards. Here I have f sub 2 minus f sub 1. Here I have f sub 1 minus f sub 2. So here, that just means that one is the opposite of the other. So that means that the integral over c of m dx is equal to the opposite of the double integral over r of del m del y dA. Okay, so this is we'll call this number 1. We'll call this the first result coming from figure number 1. So now let's consider figure number 2. We're doing the same thing. We're going around this way. It's still going counterclockwise. Here I'm going to call this C, and I'm going to call this one D. And I'm going to pull the same trick. I'm going to say start from A, go to B, and then start from B and go back to A. Now here we're going counterclockwise, so I'm going to go start from the lower one up to the upper one. And then once you get up there, come back down. So instead of thinking of this as one contour, we'll think of it as two contours that get added together. So here I'm going to just do the same thing, but with this illustration. So let's go ahead and consider the integral over C of n dy. Okay, and let me keep my illustration at hand. Let's keep that right there. We can go ahead and split this as the integral of, here, let me call this one on the left C1, since it's on the right, I mean. Let me call this one C1, since it's the first one I'm going to use. And I can call this one C2. No, Over here, I call this the one that's first. Here, let me call this one C1 and call this one C2. It doesn't matter. I just want to be consistent. I'm calling the smaller one C1. Okay, so that's my C1. And over here, I noted that I could write y as a function of x. Well, now here, I'm treating y as a variable. I'm treating y going from this to this. So let me call this a function of y. So C1, I could call it, instead of saying y is a function of x, I can say x is a function of y on this region. So here, I've already used f for something. Let me call this g. So C1, I can write it as a function x is equal to g1 of y. So I'm just writing a function of y. And same thing over here. I'll say x in this curve, in this part of my curve, is a function of y as well. Right? So I'm pretty much just pulling this, but horizontally rather than vertically. Okay, so now I can write this integral of the whole contour as just the integral of the first contour plus the integral of the second contour. So integral over C1 of n dy plus the integral over C2 of n dy. Just like that. Okay. But now I can actually quantify those, because here I know that C1 is going to go from D down to C. Note the orientation. Right? You're going to start at D down to C. Okay, so that's the integral from D to C. Now, that's backwards than what you would normally see, but that's what our orientation tells us, from D down to C, of our function, which is going to be n of, now again, n is a function of x and y, but here we've treated x as a function of y. So here we could say n of xy, but we don't need two variables. We can treat x as a function of y. So here we can write this as n of g, I'm using this one first, so that'll be g1 of y, comma y. So now it's not a function of two variables, it's just a function of one variable. It's a function of y. And this is just a standard integral from Cal 1, the integral of a function of y with respect to y from D to C. Plus, and I'm going to do the same thing over here. I have n, and n is a function of x and y, but because of the substitution here, I don't have to write it as x and y. I can write it as a function of y, comma y, namely the function g2 of y, comma y, dy. And now this one's going from C up to D. Okay, so this one's from C to D, just like that. Okay. Well, now that I have that, note that I can flip my boundaries just like I did before. It looks a little strange to have D to C, so let me flip this one. So to flip these boundaries from C to D, I have to make this the negative. So this is from negative the integral from C to D. Notice this is just a regular old integral that you would see in Cal 1 of n of g sub 1 y comma y dy plus the integral of C to D. And here I'm going to leave this one alone, n of g2 of y comma y dy. And here I can put these together. Let me put the positive one first, then the negative. So here I can write this as the integral from C to D of n of g2 of y comma y minus n of g1 of y comma y. Oh, what did I do here? I wrote g twice, didn't I? That would be n of g2 of y comma y. There we go. That's better. Dy. Okay, so now let's consider one last thing. You're being very considerate. You've considered 4 things so far. Now go ahead and consider the double integral over the region R of del n del x dA. Okay, so again, we're looking at a double integral. We're back in chapter 14. Looking at our region here, notice that this can be described, here the boundaries for y are constants. So here dy is going to be the last integral that we take from C to D. So this can be written by Fubini's theorem as the integral from C to D dy, all right? Y is the one that can be described using constants from C to D. So that's the outer bounds from C to D. Now I need to integrate with respect to x on the inner bounds. And notice that x is bound between G1 and G2, from the smaller to the larger. So this would be the integral of G with respect to x from G1 of y up to G2 of y, just like that. And here this hasn't changed. This is just the partial of n with respect to x. But notice now that I have the integral with respect to x of the differential with respect to x. Oh, that's just n, right? That's take n, take its derivative with respect to x, and then integrate with respect to x. That just brings me back to n, doesn't it? So that's going to be the integral from c up to d of n. Oh, but now we're evaluating at these bounds. Okay, well, we're evaluating x at these bounds. So here, my x is going to be g2 of y, comma y. Minus my lower bound, my lower bound, that's going to be n of g1 of y, comma y, dy. But notice that that's exactly what we got from above. So we note that the integral of c, the integral over c, rather, of n dy is equal to the double integral over r of del n del x dA. We'll call that result number 2. So now you just add these together. Note we had result number 1 from before, result number 2 now. Now add results 1 and 2. So that's going to be, let me add these together. So I'm going to get the integral over c of m dx plus the integral over c of n dy is equal to, let me go ahead and add these together. I'll put the positive one first. So this will be the double integral over r of del n del x dA. And then here that's a minus, so that'll be minus the double integral over r of del n, of del m del y dA. I've just added the left side to the left side, the right side to the right side. Oh, but now this is a line integral over the same line. So due to additivity, I can just add these together, right? Due to linearity. So here I can write this as a single line integral over c of m dx plus n dy, which is equal to, and over here, this is a double integral over the same region, right? Where we're using the same r. So that's going to be a double integral over r of del n del x minus del m del y dA. And that concludes our proof. That's what we wanted. Note that that says exactly what we wanted over here, namely that if you want to take a line integral of a vector field around that contour, here's our vector field, right, mn, and we want to integrate around that contour, that's exactly the same as if I just took the double integral of this expression throughout the inside of my integral. That may not be the most intuitive thing in the world. That might not be the obvious thing in the world, but there it is. So now let's take a look at some examples to see how that works out. And in fact, let's go ahead and start this one off on a fresh page. So let's see. Our first example, let's go ahead and find a line integral as follows. Here we want to evaluate a line integral over c of y squared dx plus xy dy, where c, they don't actually give it to us, but they give us a description, where c is the boundary of the region lying between the graphs of y equals to 0, y equals to the square root of x, and x equals to 9. taken counterclockwise. Okay. Here, let's actually just draw that out. That's going to be, let's see here. X equals to 9. That's a vertical line at 9. All right, so that'll be 9 right here. Y equals to 0. That's the x-axis. So that's this line down here, the x-axis. And y equals the square root of x is this one here, which will touch, if x is equal to 9, that means y is the positive square root of 9. So this would be 3. And so our integral is supposed to be taken counterclockwise. So that's going to go this way. And our, right, so there we go. One way to do this, of course, is you could parameterize all three of these curves. We did something similar to that in section 5.1 when we first learned about the line integrals. That is to say, we parameterize each one, and then once we parameterize each one, we can go ahead and take three separate integrals. And once we find all three, we can add them together to get our result. However, in a previous example, this wasn't necessarily closed. So that is one limitation of Green's theorem. You have to have a closed boundary here. You can't have something that starts from the origin and ends up over here and then that's it. It actually does have to loop back on itself. But as long as you have that, Green's theorem allows you to say, well, okay, you want to know stuff about the boundary? Okay, let's talk about what's going on inside. And the stuff that's going on inside will tell you what's going on the boundary. Given the way things are written out, notice this is in differential form. In differential form, this stuff right here is called m, and this stuff right here is called n. Notice they're functions of x and y. That's m of xy and n of xy. And so by Green's theorem, we have everything we need. We have a simply connected region. Notice this right here, it's not made up of multiple regions. It's not connected by individual lines or curves. It's a simply connected single region. The outer edges are piecewise smooth. Okay, there are cusps on the corners, but it can be broken into finitely many smooth pieces. 1, 2, 3 smooth pieces. And everything's oriented counterclockwise. All right. Because of that, I do satisfy all of Green's theorem. So that tells me that the integral over c of m dx plus n dy can be written as the double integral over the region R, which is the stuff inside of here, del n del x minus del m del y dA. But of course, we know what n and m are. We were given those. Those are the components of my vector field. So here, m is y squared, n is xy. So for this specific problem, we can write this as the double integral over R of, let's see, del n del x. The derivative of this with respect to x is just y, minus the derivative of m with respect to y, that's going to be 2y, dA, which is really just the double integral over R. Let's see, that's going to be y minus 2y. That's just negative y dA. Just like that. And now, by Fubini's theorem, and I'm sure you guys are tired of hearing that name by now, but he does keep coming up, doesn't he? By Fubini's theorem, we can evaluate this double integral over the area as a iterated integral. Here, I'm going to go ahead and do this with respect to y first, and then with respect to x. Remember, by Fubini's, this is interchangeable, but I personally am just more comfortable with y first than x. And really, that's just a personal preference. Here, that's going to be minus y. All right, that carries over. This is dy dx. And now we just have to describe our boundaries with respect to y first, then x. Okay, so y, remember, this can be expressed as a function of x, but these must be constants. Okay, so y goes from a low of 0 up to a high of this line up here. Notice if I'm expressing how far up and down y goes, I always go down to the same line, which is 0. But then over here, I always go up to this line, which is given by the square root of x. All right, so from 0 to the square root of x, that bounds my y. And now my x value has to be bounded using only constants. Okay, well, the lowest x value you get is 0, and the highest one you get is 9. And that is a nice, simple integral. Notice we never had to parameterize those. We never had to do any substitutions. We never had to worry about f dot dr, any of those substitutions or anything like that. Here, this is expressible as a nice, simple double integral. Here, if we integrate with respect to y, that's going to be minus y squared over 2. Okay, so let's just do that part first. That's going to be integral from 0 to 9 of, let's see, what was that? Minus y squared over 2, evaluated from 0 up to the square root of x. Dx, there we go. We can go ahead and substitute in those values. So that's going to be the integral from 0 to 9 of the square root of x squared. Well, that's just x. Here, this negative is separate. So that's going to be negative x over 2. And if I substitute in 0, that's the negative of 0 over 2, which is just 0. Okay, so here that's just going to give me the integral from 0 to 9 of negative x over 2 dy. Oh, no, it doesn't. With respect to x, I've already done y. So that's dx. And now that's a nice, pretty integral. With respect to x, the integral there is going to be negative x squared over 4. And that's evaluated from 0 up to 9. Note here that 9 squared is 81, but 0 squared is 0. So here the 0 doesn't matter. So in the end, we're going to get negative 9 quantity squared over 4. Or in other words, our line integral, without having to do any parameterizations or any of that other less than efficient stuff, we can get negative 81 over 4 as our line integral. And that's our result. Note that Green's theorem tells us something else. There's a consequence of Green's theorem. Recall, if f of x comma y is a conservative vector field, then the partial m with respect to y is equal to the partial of n with respect to x. This is something we saw back in the very first section of the chapter when we defined a conservative vector field. This was the test. This told us not what a conservative vector field was, but rather here's the test to confirm whether or not it is conservative. If this is true, then your vector field is conservative and vice versa. So I guess I shouldn't write it that way. I should write f is a conservative vector field if and only if, because it's true in both directions. So if this is equal, then this is conservative. If this is conservative, then these are equal. But notice that's if these two are equal, then del n del x minus del m del y will be 0. So thus, for a conservative vector field, Green's theorem tells us that the integral over c of m dx plus n dy is equal to the double integral over r of del n del x minus del m del y dA, which, because these are equal in a conservative vector field, is simply the double integral over r of 0 dA. And if you integrate 0, you're just going to get 0. So for a conservative vector field, this line integral is 0. But you already knew that. Let me say I did. That's right, because for a conservative vector field, line integrals are path independent. And Green's theorem applies when you have a closed contour, meaning you come back to where you started. And in the previous section, we saw that contour integrals around a closed loop, something that comes back on itself, are going to equal to 0 whenever your vector field is conservative. So here, this further confirms what we knew from previous sections. And this is just another way of looking at it. This is the same as saying that the line integral over C of f dot dr is equal to 0 for a closed curve C in a conservative vector field F. Which further confirms the third statement of our theorem, of our last theorem in the previous section in 15.3. All right. Now, this requirement that you have a closed contour, there's a little bit of wiggle room here. You say, oh, so you mean I can start from here and end up over there and that's okay? Well, not quite. There is some limitation, but there is a little bit of wiggle room. So here, without an example just yet, let's just look at a region. Okay, so let's say I have this contour here. And in keeping with Green's theorem, we're going to orient everything counterclockwise. Okay, so you say, all right, well, if that's my contour, then Green's theorem has me looking at the region in here. Yeah, but I have another contour that I'm going to be looking at. You say, okay, well, that one will be over here somewhere, and what, I can just find them separately and add them together? Well, no. Here we're going to have these interact. In fact, we're going to have one inside the other, something like this. And that'll be like that. Okay. So, wait, don't you have that backwards? Don't you go counterclockwise? This is going clockwise. Well, whenever you have something like this, when one is going in the opposite direction of another, this is still considered within the boundaries of Green's theorem. It's still considered within the conditions of Green's theorem. You say, well, what do you mean? The conditions of Green's theorem state that you have to have a simply connected region. Well, that's what I have here. I have a simply connected region, the stuff in between my curves. Okay, yeah, but what about this? This is going in the opposite direction, and they're not even interacting. They're not connected. Well, we said we have to have a simply connected region that's piecewise smooth. Well, that one looks smooth, and so does that one. Well, yeah, but again, they're separated. How do you reconcile that? Well, the other thing is look at the orientation. Let's bring this guy out here one more time. Remember that when we say that an object, that a contour rather, is oriented counterclockwise, that means that if you're traveling around it, the region in question is always on your left. And sure enough, as I'm going around here, it's always on his left. What about this stuff in here? Well, if I'm on the inner curve and I'm rotating around this way, notice that the stuff that I care about, this stuff over here, is still to his left, right? If I'm on the upper part of this inner loop, this region here is on my left. If I'm on this part, again, assuming I'm following the orientation, this region is on my left. So here, this still satisfies my conditions of Green's theorem. These are piecewise smooth because they're both smooth. I still have my region oriented counterclockwise, technically speaking, right? This is a math course. Of course, technically speaking is all we really need. And we have, well, it's not a single contour. So how do we reconcile that? How do we reconcile the fact that they're not connected? Well, basically, we cheat and we connect them anyway. So here's how we're going to do it. We're going to trace this out, and I'm going to do it in the following way. I'm going to start from here. It doesn't have to be from here, but that's where I'm going to choose to start from. And I'm going to start from this point, and I'm going to trace along counterclockwise. And that'll get me right here. Okay. Now, I haven't actually connected back to that point yet. I am extremely close to that point. I am some tiny epsilon away from that point. But before I connect, I'm going to go this way. And you say, well, no, you can't do that. That's not part of your contour. That's not part of the edge of your object. Well, you're right, it's not. But I'm not done yet. So here, I'm starting from here. I'm going up, over, down, and across this way. But right before I get to that point, I'm going to come out this way. Okay, so now once I'm here, I'm going to start going this way. Okay, so I'm going to come down and around, and I am following the requirement for Green's theorem. This is still keeping my region to my left. So I'm going to come back over here, and then eventually I'm going to get back to this point right here where I entered. Well, again, I'm not going to get to that point. I'm going to get extremely close to that point. I'm going to get to some epsilon, some unbelievably tiny number that's close to that. So now, before I touch these, I'm going to go in the opposite direction. And notice I have a line integral that is over the same region, that is over the same length, but that's in opposite directions. So if you think back to Cal 1, you think, oh, this is the integral from A to B, whereas this is the integral from B to A. These two are exactly the same, but with opposite signs. So these two will cancel out. So that'll leave you just this outer ring and this inner ring with the correct orientation. You can do this for any number of holes, for any number of things inside. So for example, if you had something that looked like this, with a hole here and a hole here, you could do that for any number of these. You could start from here, go around, oh, let's come down, let's go around, then let's come back up. All right, so now these two cancel out, and I've taken care of that hole. So now I come over here. Oh, now let me come down, and around, and then back up. And you can do that for absolutely any number of holes that you happen to need, that you happen to have in your region. So here, you're okay with any simply connected region, and that includes any that might have any number of holes in them. And there we go. So now let's apply that to a problem with some more substance to it. Let's consider the example where we want to evaluate the line integral over C of 3x squared e to the y, 3x squared e to the y dx plus e to the y dy. Where C is given by a description, the region between, let's see, the region between the squares with, and yes, I did just misspell with, didn't I? With vertices 1, 1, minus 1, minus 1, 1, minus 1, and minus 1, 1, and 2, 2, minus 2, minus 2, 2, minus 2, and minus 2, 2, oriented counterclockwise. Here, we can draw that out. It's simply, here's a square. This is 2, comma 2. This is negative 2, comma negative 2. All right, here, this would be the 1 positive, 1 negative. And then in here, we have a smaller square where this is the corner 1, comma 1. This is -1 comma -1, and again, these are the corners with the appropriate positives and negatives. And the region that we care about is the boundary as it applies to this region here. The region between that would be the boundary of the region. Right? C wouldn't be the region, it would be the boundary of this region. All right, so evaluate the line integral over C of 3x squared e to the y dx plus e to the y dy, where C is the boundary of this region here, of the stuff in between here, oriented counterclockwise. Right? Here, this justifies our ability to do this. We don't actually have to do that. We don't actually have to go through and make these cuts anywhere. It's sufficient to know that we can, and therefore Green's theorem still applies. So here, let's just go ahead and actually do it. Go ahead and give this a try. Go ahead and pause the video and see if you can describe this, instead of as a line integral, as a double integral using Green's theorem, and then evaluate using Fubini's theorem. Once you have an answer, go ahead and unpause the video, and we'll finish it off together. All right, so let's take a look here. We know that our m is this expression here, 3x squared e to the y. That's the first component of our vector field. The second component of our vector field, labeled n, is given by e to the y, just like that. And so we can find del m del y. The derivative of this with respect to y is the derivative of a constant times e to the y. Well, that's going to stay exactly the same. It's the constant times e to the y. Here, we're going to use this to find the derivative with respect to x of n. Notice that n is constant with respect to x, and therefore its derivative is 0. So here we can write the line integral over C of m dx plus n dy. Notice that is a line integral of a vector field written in differential form. We can write that as the double integral over the region R, the region inside of that contour, of del m del, I have that backwards, del n del x minus del m del y dA, which, given what we just computed, is going to be the double integral over R of, that's going to be 0 minus 3x squared e to the y. And here we can describe this with respect to x and then with respect to y, or maybe y first and then x. It really makes no difference. Okay. Well, here, let me leave this as dA since I don't have my boundaries yet. And then that would simplify to the double integral over R of negative 3x squared e to the y dA. 0 minus that is just the negative of that. So now, this is Green's theorem. And now, Fubini's theorem takes over. We can now write this, instead of a double integral, we can now write an iterated integral of minus 3x squared e to the y, integrated with respect to y, and then with respect to x. Now at this point, we have a couple of options. One is, well, we note that there's not a convenient way of expressing all of this region with just one set of boundaries. Yeah, it's true that the x values and the y values are all constants, but this kind of ruins it, because I can't really say y goes from -2 to 2, because it doesn't do that all the way through. Likewise, I can't really say x goes from -2 to 2, because it doesn't do that all the way through. So one option I could do is I could cut this into rectangles. I could say, okay, here's one rectangle, here's another rectangle, here's another one, and here's another one. And once I have these 4 separate rectangles, I could find the integral over all 4 of them and then add them together. And while that is valid, that seems a little long. what might be a little simpler is we realize, oh, if I can find the integral over this entire region, and then if I can find the integral over this smaller region, if I just subtract those, that'll give me what's left. The integral over the entire thing minus the integral of this whole will leave me the integral of just this sort of square-shaped donut here. So here I can write this as the difference of two integrals, like this, over of negative 3x squared e to the y dy dx. And now what I want to do is I want to describe the outer region as if there were no hole there. Oh, that's simple. These are all constants. That's from minus 2 to 2 and from minus 2 to 2. My y value from minus 2 to positive 2. My x value from minus 2 to positive 2. But now I want to find the double integral over this area, which is only from minus 1 to 1 and from minus 1 to 1. Just like that. And now if I find that integral and I subtract away this integral, that'll give me my double integral over this region. All right. So here, let's go ahead and see if we can't do that. That's going to be the integral from negative 2 to 2 of, looking at just this part, that's nice because the integral with respect to y of negative 3x squared e to the y remains exactly the same. Negative 3x squared e to the y evaluated from y equals minus 2 up to y equals to positive 2 dx. Which is going to be the integral from minus 2 to 2 of, if I plug in 2 here, and if I plug in negative 2, that's going to give me negative 3x squared e squared minus negative 3, so let me write that as a plus 3x squared e to the minus 2 dx. And I can do something similar over here. In fact, it's going to work out exactly the same except for the boundaries. So this is the integral from minus 1 to 1 of minus 3x squared e to the y. But now instead of from minus 2 to 2, now I have my y value goes from minus 1 to 1. And if I substitute both of those in, I get, well, let's see here, minus a minus. Let me just write that as a plus. The integral from minus 1 to 1 of, oh, let's see here. If I plug in 1 right here, that's going to be 3x squared e to the first minus 3x squared e to the minus first dx. Here, these two minuses become a plus out here. And so now I have just this, this, and if I take 3x squared e to the y and I plug in 1, it gives me that. If I plug in minus 1, it gives me this, and then I can subtract. So now we're just about done here. We need to take one more integral, this time with respect to x. So let's see, that's going to give us the, we're going to integrate with respect to x. So here that's going to raise that to the third power and then divide by 3. So that it will give us, what, minus x to the third e squared. And then the same thing will happen to this here. Plus x to the third e to the minus 2. And that's going to go from wherever x is equal to negative 2 up to wherever x is equal to positive 2. I'm just integrating both of these with respect to x. And over here, I'm doing the same thing. And in fact, I'm doing it the exact same way, except for the signs. Here, the integral with respect to x of 3x squared e is just going to be x to the third e. Remember, e is just a constant. Minus, and over here, this integral will be x to the third e to the minus first. And again, that's going to go from x is equal to minus 1 up to x is equal to positive 1. So I'm just taking these antiderivatives with respect to x and substituting in my boundaries. All right, so let's see what we get now. If we substitute in x is equal to 2, that'll give us negative 8e squared plus 8e to the minus second. Okay. And then if I substitute in a minus 2, that'll give me, what would that be? Negative 8 times a negative, so that'll be a positive 8e to the second. And then that's plus negative 8, so I can write that as minus 8e to the minus second. So I'm just plugging in those numbers. And then there's I forgot my plus sign over here, didn't I? Before I had a plus sign in between here, between these two integrals. So here I'm going to go ahead and add these two. So now that's going to be plus, that was the first one. And now the second one will be, well, we're just plugging in the number 1 here. So that's just going to be e minus e to the minus 1. And then minus, and I'm plugging in a negative 1. So that'll be minus e, minus a minus makes that plus e to the minus 1, like that. And I notice that all of these are like terms that can combine. Minus 8e squared minus another 8e squared is minus 16e squared. Here, minus a minus makes that a plus, so that'll be plus 16e to the minus second. Plus, here that's e minus a negative e, which is e plus c, that's 2e. And then negative e to the minus 1 minus another e to the minus 1 is minus 2e to the minus 1, like that. Which at this point, there's any number of ways you may want to simplify that. You can probably type that into a calculator, but that'll suffice. That looks good enough to me. No? Lastly, let's go ahead and look at an alternate form of Green's theorem. Note that Green's theorem is defined for us over a plane region. That's because Green's theorem relates a contour integral, a line integral, to a double integral. And of course, our double integrals, by Fubini's theorem, are defined on a plane. So here we have everything with respect to 2 variables. That's not a necessary restriction. In coming sections, we're going to see an extension of Green's theorem called Stokes' theorem, which will apply to higher dimensions. However, unlike most of our other theorems, the extension is not trivial. In most of our other definitions and theorems, whatever's true for 2 dimensions is clearly true for 3 dimensions or 4 dimensions. So we generally just sort of hand wave that, saying, here's the proof for 2 dimensions, and by the way, it's identical for 3 or 4 or 5. Stokes' theorem will be one of the few exceptions to that. What was proven here for Green's theorem will not easily transfer over to higher dimensions. It will, but we're going to have to work for that. However, here we're going to see something that suggests what will happen. So consider the fact that we've been looking only at vector fields in 2 dimensions. But consider that f of x comma y, which is given by m comma n, your vector field in 2 dimensions, can be thought of as a special case of f of x comma y comma z. This may exist in the plane, but a plane can be thought of as something in 3 dimensions where one of your components is always equal to 0. In other words, I can think of something on the x, y, z coordinate system, and if I want to limit myself to 2 dimensions, well, I can just consider the plane region, which we normally call the xy plane. So yeah, this is embedded in 3 dimensions, but we can consider only 2 of them. So here, consider the fact that f of x comma y, the vector field m comma n, can be thought of as a special case of a 3-dimensional vector field. Namely, it can be thought of as f of x comma y comma z is equal to m comma n comma 0, where the third component is 0. So now consider the curl of f. Of x comma y comma z. Now remember, curl is defined as a cross product, so we can't do it for something with 2 dimensions. It would have to be something in R3, a vector in R3. So here we have the curl of f, which, if you remember the notation, is del cross f. Let's consider the curl of something that looks like this. All right, well, that would be I, J, K, I, J, K. The differential operator is going to be del x, del y, del z. And then we'll repeat that. And then f is given by mn0. And then we'll repeat that as well. So now, to take the cross product, we're going to say, okay, that's I times the derivative of y, derivative with respect to y of 0. Well, any derivative of 0 is 0. So that's going to be 0i. Here, that's going to be the derivative with respect to z of m. Okay, so that's del m del z j. And over here, that's going to be the derivative of n with respect to x as my third component, del n del x k. Just like that. And now going back in the opposite direction, that'll give me minus each of these. That'll be del n del z for my first component, del n del z I. For my second component, I'm going to take the derivative with respect to x of 0, which of course is just 0, so we don't worry about that. And here we're going to take the partial of m with respect to y as my third component. The partial of m with respect to y of my third component. So now when I put these together, that's going to give me 0 minus del n del z as my first component. So that'll just be negative del n del z. Del m del z minus 0. Okay, so that'll give me positive del m del z. And then here, that's for my third component, del n del x minus del m del y, which you'll recognize as being the argument of the line integral, of the double integral given by Green's theorem. You'll recognize that as being this integrand here. So that third component is the integrand that I want. So we can write Green's theorem by writing that third component. The way we write that is we can say that's, how do we want to write that? Del n del x minus del m del y is equal to the third component of the curl of f. So we can write this as curl of f dot with 0, 0, 1. Because remember how the dot product works. It'll be this times 0 plus this times 0 plus this times 1. Or in other words, just this one. This is also sometimes written as the curl of f dot the vector k. Because remember, k is the third component of a vector. So the vector k would be the vector, the unit vector 0, 0, 1. So here, this is just an alternate notation for that. And so Green's theorem can be written as the line integral over c of f dot dr, which is the line integral over c of m dx plus n dy. All right, so here these are just the vector field notation and the differential notation. That's equal to, by Green's theorem, the double integral over r of del n del x minus del m del y dA. And by this result, that can be written as the double integral over r of the curl of f dot k dA. This is the alternate this is an alternate notation for Green's theorem. And this is what will eventually extend into what's called Stokes' theorem. The curl of f is something a lot more meaningful than we've let on. Up to now, it's just been a computation to get us whether or not whether or not a vector field is conservative, so we can find some nice results from there. But the curl of f will actually be a lot more meaningful. Notice that just one component of the curl of f gives us Green's theorem. When we take all three components, that'll yield Stokes' theorem, which will come at the end of the chapter. But this gives us an introduction to that, and it also gives us an alternate notation. This is another way you might remember Green's theorem. And so that brings us to the end of our section. Let's see, for an assignment, you should probably practice some of these, especially given how much time these tend to save. These can be very efficient, assuming, again, that you're in a closed contour that's oriented counterclockwise. Here, go ahead and try section 15.4, problems 11 through 27 odd. Just like that. And that should suffice. If anybody has any questions or problems or comments, make a note of those and reach out to me, and I'll get back to you as I can. And I hope everyone has a nice day.